Hi all, welcome to chemakhilam Field the Chemistry. Last video we were discussing about ESR or EPR spectroscopy. In first video we discussed about the general thing, that is what is meant by ESR spectroscopy and which kind of molecules shows these spectroscopy and number of lines we are getting. In second video we discussed about the intensity of spectral line, that is using Pascal triangle and using non-Pascal triangle. If you did not watch those videos, please check the description box. Also you can check the playlist named spectroscopy. In that folder you can see number of videos related to spectroscopy. In today's video we are going to discuss about ESR spectrum of transition metal complex, and it is very important. Here we are discussing about Drago's rule, and it is very important in exam point of view. Also we are discussing about zero field splitting, what is meant by Kramer's degeneracy, and also another important part, that is number of fine lines and hyperfine lines. In almost all question paper, if the question is from ESR spectroscopy, then number of fine lines or hyperfine lines normally asking. So now we can go to the video. Okay, the ESR spectra of transition metal complex we can discuss in two headings. First heading is metal having one unpaired electron, and second, metal having more than one unpaired electrons. In that part we are discussing about the Kramer's degeneracy. Now we can discuss in detail the metal having one unpaired electron. When here we can discuss three cases. In first case, when the metal and ligand both are inactive. Okay, when the metal having one unpaired electron, also the metal and ligand both are inactive. We discussed in our previous video that the compound should contain an unpaired electron, then only it will be ESR active. So here we are discussing on the metal having one unpaired electron, so it is ESR active, and the splitting is caused by metal and ligand. If both are inactive, what will be the case? When metal and ligand both are inactive, that is Im equal to 0, Il equal to 0, and Is equal to 1 by 2 means it contains one unpaired electron. That is what Is equal to 1 by 2. And you know that there will be 2I plus 1 degenerate level. Then here I value is 1 by 2, so 2 into 1 by 2 plus 1, that is 2. Then here 2 degenerate level will be there. That is, in the absence of magnetic field, there will be two levels, that is plus 1 by 2 and minus 1 by 2. When magnetic field is applied, this degeneracy breaks and it will split into two levels. One is minus 1 by 2 level, other is plus 1 by 2 level. So here only one transition is possible, that is what this thing. Here two degenerate level will be there. In the presence of magnetic field, it will split into two levels. One is minus 1 by 2, other is plus 1 by 2, and only one transition is possible. That means number of lines will be 1 and there will be no splitting. This is the case when both metal and ligand are inactive. And both metal and ligand are inactive, there will be no splitting. Number of lines will be 1, as we have only one unpaired electron. Okay. In next case, either metal or ligand is active. Either metal is active or ligand is active. In that case, we can write as Im not equal to 0, Il equal to 0, Is equal to 1 by 2. Here metal is active, ligand is inactive. And next case, Im equal to 0, Il not equal to 0, Is equal to 1 by 2. Here metal is inactive and ligand is active. Okay, here metal is active, here ligand is active. Here ligand not active, here metal not active. In that case, how this splitting will occur and how many number of signal we are getting? Okay, as any of the nuclei is active, there will be splitting, that is sure, and that splitting will be 2Ni plus 1. Now we can consider an example, Cu L4 2+. Here copper complex, 4 coordinated complex. Cu2 plus is having a D9 configuration, so there will be one unpaired electron, that is sure. So there will be one signal. It is ESR active as it contains one unpaired electron. So it is ESR active. How the splitting will occur? Number of lines will be 1. Here metal is active. The Cu2 plus have an I value of 3 by 2. So splitting occur 2Ni plus 1 times 2 into 1 into 3 by 2 plus 1, that is equal to 4, and the intensity is 1 is to 1 is to 1 is to 1, and this intensity is based on non-Pascal triangle that we discussed in our previous video. As I value is greater than 1 by 2, the intensity we can discuss or we can explain using non-Pascal triangle. When I value is 1 by 2, we are using Pascal triangle. When I value is greater than 1 by 2, we are using non-Pascal triangle. How we are getting this intensity that we discussed in detail in previous video, please check that one. Here metal is active, ligand not active. Here we are getting 4 lines and the intensity is according to non-Pascal triangle. Next, another example, Ml6 plus. Here we are considering that metal is inactive and ligand is active with a spin of 1. Okay, this is an assumption. Here unpaired electron is 1. We are assuming that number of unpaired electron is 1, so the number of lines will be 1. Splitting, in the case of splitting, the metal is inactive and ligand is active. Ligand have an I value of 1. So splitting will occur in 2Ni plus 1 times 2 into, here 6 ligands are there, 2 into 6 into 1 plus 1, that is 13. Number of signal will be 13. When both metal and ligand are active, that is when Im value not equal to 0, Il value not equal to 0, and S equal to 1 by 2. S equal to 1 by 2 means there is an unpaired electron. When both the ligand and metal are active, both will split separately in 2Ni plus 1 times. Now we can consider one example, copper NH3 4 times 2 plus. Here Cu2 plus is D9, that is it have one unpaired electron, so number of signal will be 1. How the splitting will come? Here 3 nuclei are there, one is copper, other is nitrogen, other is hydrogen. So 1 copper, 4 nitrogen and 12 hydrogens are there. I value of copper 2 plus is 3 by 2, I value of nitrogen is 1, I value of hydrogen is 1 by 2. So splitting will be first according to copper, then with nitrogen and then with hydrogen. So the value will be 468. Actually this much value does not comes. The number of splitting will be only due to copper and nitrogen. Here hydrogen is not participating splitting, only copper and nitrogen are participating splitting, and here we are getting a value of 36. That is the actual number of lines that we are getting for this compound. Why it is so? And it is explained using one rule that is known as Dragos rule, and Dragos rule is very, very important in the case of transition metal. So we can discuss more about Dragos rule. Dragos rule states there, or it have a postulate that hydrogen attached to magnetically active nuclei don't participate in splitting. That is, when hydrogen is attached to an active nuclei, those hydrogens will not participate in splitting. When hydrogen is attached to an inactive nuclei, those hydrogen will participate in splitting. And this rule is applicable only to transition metals. In the case of transition metals only, this rule is applicable. If a magnetically active nuclei is present, the hydrogen attached to it will not participate in splitting. If an inactive nuclei present, hydrogen attached to that inactive nuclei, those hydrogens will cause splitting. This is what Dragos rule, and it is applicable only to transition metals. Now we can consider the same example. Here nitrogen is an active nuclei, thus hydrogen not participate in splitting. So only copper and nitrogen cause the splitting, and we are getting a line, number of lines 36. Okay, here nitrogen is an active nuclei, so hydrogen will not participate in splitting. So here copper 2 plus, that is it contain one unpaired electron, so number of signal will be 1, and the splitting will caused by both copper and nitrogen. Here hydrogen will not participate in splitting, and we are getting a value of 36, that is the number of signals. Clear? Next we can consider another example, that is copper H2O 6 times 2 plus. This is an octahedral complex, aqua complex. Here this is the structure. Here two types of hydrogens are there. Copper 2 plus means it is D9 configuration, so it will undergo Jahn-Teller distortion. In why we are not considering here, this is but the coordination number is 4, and Jahn-Teller distortion is in octahedral complexes. Here two types of hydrogen will be there, one is axial, other is equatorial. Okay, here oxygen is not an active nucleus, so hydrogen will split. Oxygen is not an active nucleus, so hydrogen will cause splitting. Here two types of hydrogens are there, it is due to Jahn-Teller distortion. Axial hydrogens are there, 4 axial hydrogen, and 8 equatorial hydrogens are present. So the splitting will be first due to copper, next due to hydrogen. Here oxygen is not an active nuclei, so hydrogen will participate in splitting. And here as it is D9 configuration, and it will undergo Jahn-Teller distortion, two types of hydrogens are there. So the splitting will be first due to copper, that is 2 into 1 into 3 by 2 plus 1. Next due to axial hydrogens, 2 into 4 into 1 by 2 plus 1. Next due to equatorial hydrogens, 2 into 8 into 1 by 2 plus 1. Overall 180 is the number of signals. I think it is clear. Drago rule is very, very important. From these two examples, I think it's very clear how to calculate the number of signal. If an active nuclei is there, you don't consider hydrogen. If that nuclei is not active or it's an inactive nuclei, consider hydrogen. That is the rule, and very, very important thing, it is applicable only to transition metals. If some other compounds that is not a transition method, don't apply this rule. Okay, if some other compound will be there, don't apply. If aluminum, some complex if given, aluminum is not a transition metal, so in that case you have to consider nitrogen splitting, also hydrogen splitting. You have to consider hydrogen splitting, and oxygen will not split. That's okay. Okay, but this is applicable only to transition metal, and hydrogen attached to a magnetically active nuclei will not participate in splitting. If it is attached to a magnetically inactive nuclei, those hydrogen will participate in splitting. Now we can move on to next category, that is metal having more than one unpaired electrons. In that case we have to discuss about Kramer's degeneracy. Now we already discussed about one unpaired electron. Here we have to consider more than one unpaired electrons. Okay, when more than one unpaired electron present, the degeneracy of spin energy level get broken before the application of electric field, which is known as zero field splitting. Okay, in previous case we consider one unpaired electron, so it will have a degenerate level, like that we told 2i plus 1 number of degenerate level will be there. So it will split in the presence of magnetic field into 2. Then we are getting one signal, like that we discussed before or starting of the video. Here it is telling that before applying that magnetic field, the lines will split. That is known as zero field splitting. Okay, spin energy levels of same spin quantum number will remain degenerate during zero field splitting. let's consider one example, then it will be very clear. If this much lines are not needed, simply by figure you will get an idea. Now consider 5 unpaired electrons. So degeneracy will be 5 unpaired electron means I value will be 5 by 2, right? 5 into 1 by 2, that is 5 by 2. So degeneracy will be 2s plus 1 or 2i plus 1. Then it will be 2 into 5 by 2 plus 1, that is 6. 6 degenerate level will be there. That is what I represented here. The levels will be plus or minus 2, plus or minus 3 by 2, plus or minus 5 by 2, plus or minus 1 by 2, plus or minus 3 by 2, plus or minus 5 by 2. Overall 6 degenerate level will be there. So before applying the magnetic field, these lines will split like plus or minus 1 by 2, plus or minus 3 by 2, plus or minus 5 by 2, like that it will split. This is known as zero field splitting. Without the application of an electric field, or without applying the field, the degenerate level split into different level, that is known as zero field splitting. And these pairs known as Cramer's pairs. Here 3 Cramer's pairs are there. Okay. Now we have to consider how it will cause the, or how many lines we will get. That is what we have to discuss. Here degenerate level will be there. So before applying field, it will split into some set of lines or some set, and that is known as Cramer's degenerate levels, or that is Cramer's pair. And here we are getting 3 Cramer's pairs, that is plus or minus 1 by 2, plus or minus 3 by 2, plus or minus 5 by 2. Now we have to apply field, magnetic field. So it will split like this, minus 1 by 2 plus 1 by 2 will split, and like that the splitting will cause. Now we have to find out number of lines. So for that we need one selection rule, and that selection rule will be delta ms equal to plus or minus 1. Using this selection rule, we have to find out how many lines are possible during this transition, or using this 5 unpaired electrons, how many transitions are possible in the case of 5 unpaired electron in presence of magnetic field. Okay. Now the selection rule is delta ms equal to plus or minus 1. Here we can start from minus 1 by 2. Minus 1 by 2 minus 1 is minus 3 by 2. That is what the first line. Minus 1 by 2 plus 1 is known as, or it will give plus 1 by 2. So the line number 2. Next, minus 3 by 2 minus 1, that is minus 5 by 2. Minus 3 by 2 plus 1, it is minus 1 by 2. So that is lower level, and that line we will not consider. Next, plus 1 by 2 plus 1, that is plus 3 by 2. Plus 3 by 2 plus 1 is plus 5 by 2. So overall we are getting 5 lines, 5 number of lines. Here we consider that we have 5 unpaired electrons, and that will give 5 signals. So number of fine lines will be number of unpaired electron. Number of fine lines will be number of unpaired electrons, and number of hyperfine lines will be number of unpaired electrons into 2n1 I1 plus 1 into 2n2 I2 plus 1. Okay, this is what means. This is splitting caused by the ligand or metal, like that. Here number of fine lines will be number of unpaired electrons. Number of hyperfine lines means number of unpaired electron into that number of splitting, that is 2ni plus 1. Okay, these two things are very, very important. You have to note down and you have to work on it. I think in almost all exams they will ask number of fine lines or number of hyperfine lines. Don't you should remember that number of fine lines will be number of unpaired electrons, and number of hyperfine lines means that is due to splitting. Okay, 2Na plus 1, that magnetic splitting due to magnetic nuclei, splitting due to d ligand, those things we have to consider in hyperfine lines. Number of fine lines means only number of unpaired electrons. Okay, now we can consider one example, that is trans titanium NH3 twice, H2O 4 times 2 plus. Here this is the compound titanium trans, it is trans, so 2NH3 will be in the axial position and H2O will be in the equatorial position. So here the hydrogens in H2O, these are in same environment, so it will give the same signal. Okay, here nitrogen is an active nuclei, so NH hydrogen will not participate in splitting. Also oxygen is not an active nuclei, so OH hydrogen will participate in splitting. Okay, here nitrogen is an active nuclei, so these hydrogens won't participate, this 6 hydrogen won't participate. Here oxygen is not an active nuclei, so here 1 2 2 4 6 8, these 8 hydrogens will participate in splitting. Okay, then titanium having a titanium 2 plus having a configuration of D2, so the number of unpaired electron will be 2. So the number of signals we have to find out. So I have titanium 2 plus have an I value of 3 by 2, nitrogen have an I value of 1, hydrogen have an I value of 1 by 2. So number of fine lines is number of unpaired electron, and that is equal to 2. Okay, in option they will give 2 and the splitted number, everything they will give. So remember this thing, number of fine lines means number of unpaired electrons. Okay, number of fine lines will be number of unpaired electron, and number of hyperfine line means number of unpaired electron. Also we have to consider the splitting caused by the nucleus, active nucleus. Okay, here hydrogen, nitrogen and hydrogen. Here hydrogens of nitrogen won't participate, also hydrogens of oxygen will participate. Okay, now the splitting will be 2 into, here 2 means unpaired electron, 2 into 1 into 3 by 2, that is splitting caused by titanium. Next 2 into 1 plus 1, that is splitting caused by nitrogen. Here these 6 hydrogen won't participate, and then 4 oxygen won't participate, then overall 8 hydrogen, those will participate. 2 into 8 into 1 by 2 plus 1, overall 360 is the number of signals, and number of hyperfine lines means 360, number of fine lines will be 2. And this you have to remember, fine lines means unpaired electron, hyperfine line means unpaired electrons into splitting caused by the active nucleus. I think it is clear. Drago rule is very important. Also number of fine lines and hyperfine lines is very, very important. You have to work it using some examples. You have to work on it. Okay, if you have any doubt on this video, please comment. And if you like this video, like, share and subscribe, and you can follow me on Instagram, Facebook. Also you can mail to me if you have any queries. Please press the bell button to get notification when I am uploading video. Thank you for watching.